Hello there. So let's take a look at experiment number 8, the copper chloride hydrate formula. So in the lab, we've got a bit of a detective story for the lab this week, trying to work out the correct formula for the copper chloride hydrate. You're going to take mass measurements of each of the components, copper, chlorine and water. You can use a periodic table to convert that into molar quantities. That can be simplified to what we call the empirical ratio, just the simplest form of the chemical ratio. So for example, if you got something like 4, 4 moles of copper, 8 moles of chlorine and 4 moles of water, the empirical simplest formula would just be 1 to 2 to 1. Take the smallest component or equal smallest component and divide everything by the smallest component. That gives the simplest version of the ratio. Now remember, we have water in the formula, but it's not really part of the chemical formula. Our compound is just hygroscopic, which means to say that it just naturally soaks up water. So we can emphasize that this is water of hydration by putting in that period, or full stop as we would say in Britain, putting in the molar quantity and then the formula for water. This is water of hydration. So, first step is going to be to dry your copper chloride hydrate. Drive off the water with a bit of heat from a Bunsen burner. Make sure you have the hotter blue flame, and you're going to set up your sample inside a crucible. Set it inside a clay triangle. That clay triangle will wrap around the edges of an O-ring, which in turn will be clamped to one of the clamp stands in the laboratory. And then just use that blue flame from the Bunsen burner to just lightly heat the very bottom of the crucible. So as your sample dehydrates, as it loses water, you'll see the colour of the sample change from a blue-green colour to this kind of soil brown colour. That's the colour of the copper chloride when water has been driven off. And that should take less than 5 minutes. If you hear your sample crackling, you're heating it too much, take the heat source away. And when you think you're done, take away your Bunsen burner heat source, and then with a metal spatula just dig around in the sample and make sure there's no blue-green colour buried underneath. Make sure that you've driven off all the water. You can put the crucible lid back on, give it another 5 minutes to cool, and then carefully take over to the balance to measure the mass of the remaining sample. Remember, if your initial mass was with the crucible lid, then your new mass should be with the crucible lid on. Otherwise, you're going to add or remove the weight of the lid itself. So initial mass minus the now dried mass, that should be the mass of water that was in the sample. So that copper chloride is now put back into water, which rehydrates it, and you're going to get a redox reaction to take place between copper and aluminum. It takes about 25 to 30 minutes. You'll know when it's done because that bubbling should be finished in the solution. The aluminum is oxidized into aluminum ions, which dissolve into the water solution. They're giving away electrons to the copper ions in solution, and as the copper accepts electrons in the reduction, it precipitates out on the surface of the aluminum wire as copper metal. You'll see it start to build up, and just shake it and scrape that aluminum wire a little bit every so often to shake off the copper, freeing up more aluminum surface for more redox reaction to take place. The aluminum surface and the copper ions in solution need to be able to be in contact for that electron transfer, oxidizing aluminum, reducing copper. Now of course we have two different charges for copper, and it depends on the actual chemical formula for the copper chloride hydrate. If it's the higher charge of copper, 2 plus, the cupric, then it accepts 2 electrons each time from the aluminum to become copper metal. But if it's a lower charge of copper in the copper chloride complex, it accepts just 1 electron, accepting electrons to the cuprous to again precipitate out copper metal. You'll have to look at your final calculated chemical formula to realize whether it was the 2 plus or the 1 plus that was reacting in the redox. Now, you can collect that copper by vacuum filtration. Now, some of the stations we have this week probably won't have this second station. You'll probably have just a Erlenmeyer with a Buchner funnel and connect it directly up to the vac line. If these second Erlenmeyers are available, they are useful because it helps to stop solvent being sucked up into the vacuum. But we have very few of these left because of breakages. Put a piece of filter paper in the Buchner funnel. Make sure it sits flat on the bottom of the Buchner funnel. That way, when you pour in your solution, none of the copper should slide underneath the filter paper. Turn the vacuum on. You will drain off the initial water solution. You can then add in some hydrochloric acid to dissolve any remaining aluminum on the filter paper. Then use the vacuum again to drain that off. That hydrochloric acid and water solution can then be poured into the waste, connect back up to the vacuum, and then put in some methanol. Methanol has a lower boiling point than water or hydrochloric acid, so it's going to be easier to dry the copper if we're draining off methanol. Leave the vacuum on for about 5 minutes to help dry the copper, but to completely dry the copper, you're going to have to put your sample in the oven. Stick it in a beaker with the filter paper and dry in the oven for 5 minutes at a time until you get a constant mass. Now, of course, that means, therefore, you're going to have to put it into the oven for at least 2 sessions. Check the weight on the second session compared to the first. If there's a change in mass, you're still removing water, and it might therefore still be wet. Only when the mass becomes constant from one reading to the next will you be confident you've driven off all of the water. That's important, otherwise you'll overestimate the weight of the copper and it will cause problems with your final chemical formula. There'll be too much copper and not enough chlorine and water in your calculation. Now, chlorine is the only component that we can't measure directly. We can't separate that from the aqueous solution. So that original mass minus the mass of water recovered minus the mass of copper should be the weight of chlorine in your original sample. So let's take a look at the calculations we need for the chemical formula. You've got those initial masses that you've recovered for copper and water, and you've deduced the amount of chlorine that must be present from the original sample based on that. Now, these are just example figures I've made up. I'm just going to use them to come up with a chemical formula so you can see how we get there. Now, of course, a chemical formula uses molar proportions, not mass proportions. So we can divide each component by the molar mass to work out the number of moles. So the 0.29 grams of copper divided by the molar mass of 63.54 to give us 0.00456 moles of copper. The chlorine recovered divided by 35.45 to give us 0.0197 moles. And the 0.31 grams of water divided by the molar mass for water, 18 grams, to give us 0.0172 moles. Now, of course, a chemical formula has whole numbers, and we can convert this ratio, this molar ratio, into a nicer whole numbered ratio just by taking each and dividing by the smaller answer. In this case, copper. So divide each of the three components by that 0.00456 moles of copper. So the smallest dividing itself will give us 1 mole. The smallest dividing the number of moles of chlorine will be 4.33 moles in this example. And the smallest dividing the number of moles of water will be 3.77 moles. Now the experiment is crude, so you're not probably going to hit an exact whole number. So you can then appropriately round down in the case of the chlorine, or round up in the case of the water, to get a molar ratio of 1 to 4 to 4. We can then put that into a chemical formula. 1 mole of copper, 4 moles of chlorine, and 4 moles of water as water of hydration. Remember our period there. Now that we have the chemical formula, we can also make a stab at the chemical name for this compound. Remember, copper has 2 possible charges, 1 plus and 2 plus. The 4 moles of chlorine, because chloride is -1, would imply that the copper charge here is 4 plus. Of course, we don't have a 4 plus charge for copper, so we've got some experimental error here. But the 2 charges we do have, 1 plus and 2 plus, the best we can do is go with the idea that this is the higher of the 2 charges for copper, so we'd name it as cupric. We've got 4 moles of the chloride. Remember that IDE ending for the latter element. And for 4, that's tetrachloride, as we talk about in the notes. Also 4 moles of water of hydration, so tetrahydrate. Cupric, tetrachloride, tetrahydrate. Now this is just my example using a completely random set of figures. The important part is that you follow the same technique to get to your answer. Good luck, and as usual, just let me know if you have any questions or need help.